So that's my path, and if let's get into now the difference between quality and industrial engineering and what each of those provide. When people ask what I do for a living, my response is I'm an organizational leader, and I mentor operational excellence. And what I mean by operational excellence is it's a combination of quality engineering and industrial engineering. Quality engineering, or the buzzword is Six Sigma, is about reducing variation and making things more consistent. And industrial engineering, and the buzzword for that is lean or lean manufacturing, that's all about eliminating waste and reducing cycle time and reducing inventory and lead time. So they're alike in that they both improve, and they're different in that they have different applications and ways of improving. So what I'd like to get into now is the difference between the two of them. So for quality engineering, or as you can see here, Six Sigma, the big buzzword, is well, what is it? What is quality? And the question I would ask is it inspection? You hear these ads on the radio about, the car's been through a 40-point inspection and it's going to be good and ready to go. And that seems like a good thing, but to me, not necessarily. For example, count the number of letter F's in the gray. Okay, ready? You got your number? There's actually, well, I counted 6. A lot of people would only count maybe 3. The tough ones are always the of. People skip over the of. The point of this exercise is, out of a classroom of 10 people, you'll probably get about half of them with different answers. So inspection is not always 100% accurate. So quality is not inspection. Quality is actually designing and building quality into products rather than inspecting quality into the product. And there's ways of doing that. When you design quality in, you actually take customer inputs or customer feedback, and then you translate those things into design outputs or product features. That's the way you build quality in, and then you take those designs, or design quality in, you build quality in through creating controlled and consistent processes, and you optimize those processes that meet the customer inputs. And then from there you can improve upon it. So in other words, as you build your product for your customer, you're going to get it pretty good starting out, but there's always room for improvement, and you do that through problem solving. You do that through defect reduction and cycle time reduction. So the goal is not just to have a quality product, but also a quality product that people can afford. That's where the cycle time reduction comes in. So you can see there's a link there: design, build, and improve, and it's a continuous cycle. Because maybe after you improve the process and continue improving, maybe on the next upgrade in design, you take that feedback and you design it into the new product or upgraded product, and it's a continuous cycle. Here's a tool that I'd like to share. This is called Statistical Process Control. This is where you actually measure data from a product feature, and you document it. So as a process is running, you can take this information, collect it, and then you can create what's called an SPC chart, or Statistical Process Control chart. And what this does is it predicts statistically if something has changed. Change can be good and it can be bad. Something could change for the better. In other words, it could change towards meeting customer specifications, and it can change for the worse. It could go away from meeting customer expectations. So the goal of this chart, you're going to have random variation in a process. But if something is significantly different, you can trigger it using SPC. There's a handful of tests that you use to say, is this statistically significant or not? And the reason that's important is you don't want to be adjusting your process every 5 minutes to try to hit a target. A process is going to naturally have variation, and the goal of SPC is to control that variation to the point that you don't need to be adjusting the dials. You just let the process run. And then when there's significant change, you investigate that change. Process capability, this is very similar to SPC. What it does is it compares your histogram of where your data is falling. If we take that previous example, all those data points, and we compile them in what's called a histogram, we can compare that histogram to the specifications. And you can see statistically, you can actually calculate a probability of getting a bad part. You can see there's a small probability here of we have product going out of the lower spec limit, whereas the upper spec limit, the probability is less. And another example, this one's a little bit more centered. So you can see the power of improving a process. If you can center it more, you'll have less defects going out the lower end and upper end. Design of experiments is really neat. When you do a science fair project in school, they always say you have a control and then a variable. Well, with design of experiments, it allows you to have many different factors and move them through a design test. And then you can get an output that can be very powerful, and it can be very profound. For example, let's say the customer wanted your data to be at 0.08128. That would be at this point right here. Now, if you want your process to hit that number, you would set your mold temperature at 185, so that's your top bar here. You'd set your melt temperature at 715, because that's this bar here, and you'd set your hold pressure at 350, the third dimension, your hold pressure 350. So you know the process settings to optimize to the customer specifications. And this is all done through testing and replications and things like that. But it's a very neat tool that can tell you profound knowledge about your process.